Hi, my name is Pedro Santos Goncalves. I'm an associate professor at Lusófona University in Lisbon, Portugal. Together with my colleague, Professor José Carlos Dias Rocco, we recently published the paper Chaotic and Stochastic Components in an Influenza Surveillance Series Nonlinear Dynamics and Predictive Modeling Study in JMIRX Med. In our paper, we apply recent methods from chaos theory and topological data analysis to epidemiological risk and surveillance, specifically to influenza data. So chaos theory deals with randomness that has an origin in a system's nonlinear dynamics, that is, randomness with a deterministic source, and is characterized by sensitive dependence upon small fluctuations. That is, a small fluctuation is amplified with time, leading to a divergent trajectory. This is the so-called butterfly effect, and this is called deterministic chaos. However, empirical studies on chaos require distinguishing between the randomness that comes from the system's own nonlinear deterministic dynamics, which is this deterministic chaos, and the randomness that comes from an external noise source. But in general, empirical studies on chaos deal with chaotic dynamics that is affected by dynamical noise, which corresponds to the concept of stochastic chaos. So stochastic chaos is chaos, deterministic chaos, but when deterministic chaos is affected by external random factors, so dynamical noise, we have this concept of stochastic chaos, where the butterfly effect is still present. So a key feature of chaotic dynamics, be it deterministic or stochastic, is that while there are limits to predictability, machine learning and topological methods can be used for prediction, exploiting key features of chaos, which is an underlying recurrence structure that can be used for forecasting and also for risk analysis and management. In epidemiology, which is the context of our paper, chaos theory was mainly researched with respect to theoretical mathematical epidemiological models, so models of contagion that were found to lead to chaotic dynamics. So, empirical research into chaos, however, and we have this theoretical research already well established, but empirical research into chaos in epidemiology expanded more recently, and mostly during the COVID-19 pandemic, largely because of the unprecedented availability of epidemiological data during that period. And several studies did report evidence of underlying chaotic dynamics in COVID-19's epidemiological surveillance series. By comparison, empirical studies of influenza surveillance remain relatively fewer, and our objective was to help bridge this gap by researching whether influenza outbreaks are completely random or whether they are driven by hidden deterministic and stochastic dynamics that can be identified and used to support both epidemiological modeling and epidemiological surveillance. From the standpoint of epidemiological risk, a basic implication of chaos, if present, is that policymaking may have non-trivial, non-linear consequences on the dynamics, including the possibility of triggering chaotic dynamics and turbulent bursts, or even reduce them, as took place during the COVID-19 lockdown for the influenza series that we analyzed. In our paper, we applied a recent method that employs machine learning and topological data analysis for chaotic attractor reconstruction from time series data, and able to capture both the nonlinear deterministic component and the stochastic component, specifically developed for stochastic chaos modeling and aimed at risk analysis applications. So working with the weekly share of positive influenza tests on for the Northern Hemisphere from January 2009 to March 2025, compiled by our World in Data using FluNet data from the World Health Organization, we found evidence that influenza dynamics can be understood as the interaction between two complementary processes. The first is a chaotic process that shapes the overall evolution of outbreaks, and it is the dominant process. The second is a stochastic process with time-varying volatility that governs the uncertainty associated with those outbreaks. So we don't have chaos affected by white noise, which is the traditional context where stochastic chaos has been researched within mathematics, we have a more complex process here. And this result is relevant because it suggests that epidemiological surveillance should account not only for the expected evolution of disease activity, but also for the changing volatility surrounding it. By capturing these two components together using machine learning, we show that it is possible to support accurate prediction with high R-squared scores for up to 5 weeks ahead for the Outbreak series, while providing a richer framework for epidemiological surveillance, outbreak risk analysis, and public health decision making. So, our results reinforce the theoretical studies that have found chaotic dynamics to be possible in basic epidemiological models. However, the type of stochastic chaos is more complex since it is affected by noise with non stationary variance and outbreak waves visible in the surveillance series under study tend to occur in tandem with a rise in noise variance. So we have this dynamical noise affecting influenza epidemiological nonlinear chaotic dynamics with a non-stationary variance that increases in outbreak periods, leading to and amplifying turbulence bursts in those periods. Turbulence bursts that are already present in the chaotic dynamics itself, which is characterized by intermittent chaos. Um, but the noise process effectively injects short-run fast turbulence and intermittency into the chaotic attractor's longer range dynamics and lead to stochastic turbulence leaks into the chaotic dynamics itself, which is, as we stated, itself turbulent, this chaotic dynamics. More broadly, our results reinforce the growing role of chaos theory and complexity science in epidemiology. They also suggest that combining nonlinear dynamics, uh, topological data analysis, machine learning, and statistical modeling can provide new insights into the mechanisms underlying infectious disease dynamics and contribute to more effective epidemiological surveillance, prediction, and risk analysis. So we chose to submit our research to JMIR Med because of its strong commitment to high quality interdisciplinary research at the intersection of medicine, epidemiology, data science, and digital health. We also greatly appreciated the rigorous editorial and peer review process, as well as the guidance and expertise of the academic editor, which significantly strengthened our study. We also liked the process by which the peer reviewing is published alongside the paper. So we have this paper published and the peer reviews and the author's responses to the peer review, then which is, in our perspective, adds to the robustness of the scientific work and to the overall debate and reflection around scientific work. So we are grateful for the opportunity to communicate our findings to an international scientific community. Thank you for your interest in our work.